In a pile driver shown in the diagram, a hammer is pulled upwards and then released to fall and hit a pile. So the force produced by the hammer in a vertical direction drives the pile into the ground. Tung, 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 tung. So have you seen this? Okay. When a hammer lifted to a height h from the Earth's surface possesses gravitational potential energy. Gravitational potential energy is the work done to lift an object to a height from the Earth's surface. So this is the definition of gravitational potential energy. So when you are asked about if you, let's say in an exam, or you are shown this diagram or any diagram related to gravitational potential energy, and the question asks you what is the energy possessed by this object. For example, this time the hammer, what is the energy possessed by the hammer? So the answer must be gravitational potential energy. You cannot only say potential energy, because potential energy has two different energies, which is gravitational potential energy and elastic potential energy. We will look at elastic potential energy after this. So let's get back to gravitational potential energy. Gravitational potential energy is equal to mgh, where m is the object mass, unit must be in kg, g is the gravitational acceleration, the unit is meter per second squared, and h is the height, and it's in meters. Just to remind you what is weight, so usually we talk about mass. So when you want to get weight equals to m times g, where g is estimated to be 10 meter per second squared. Relationship between work and gravitational potential energy. Work done, we have learned this one, and this is the formula, which is force times the distance, where the distance has the same direction as the force. So if we have weight as the force, we just time with the height. So weight, just now we talk about weight. Weight is mass times gravitational acceleration. When we substitute this as weight, so we have this formula mg from the weight, and h is the distance. So you don't need to really memorize. Okay, so it's actually from here. Now look at this diagram. So a person is holding an object. If the object is falling, or sorry, a person is lifting an object. So the object is at a new position here, which is at h meters from the ground. So since there is no other form of energy produced, all work done on the object will be converted to gravitational potential energy. So you now can calculate GPE, which is equals to work done, which is equals to mgh. So what is the relationship between work and gravitational potential energy? So the relationship is gravitational potential energy is equal to work done. So let's look at this example. Okay, how much work is done by this lift? and mass is 500 kg and G is 10 and H is 30 meters. So the relationship is, yes, we discussed that already. The relationship is equal. Why is work done? Yup, that's true. Because the spring moves the staples in the direction of the force. So there is work being done. Where does the energy that carries out the work come from? Now, work done to compress or stretch an elastic material over a displacement of x from the position of equilibrium. So that is the definition of elastic potential energy, and this is the formula of elastic potential energy. Now we look at a relationship between work and elastic potential energy. Elastic potential energy equals to work done. So the relationship is elastic potential energy is the same as work done. So if we have a graph like this, so we plot the graph after we do experiment. Okay. So when we have this line, this graph, under the graph is an area. So this region or the area under the graph is equals to work done. So what is the formula of the area? So the area is in the shape of triangle, and you know the formula of a triangle, which is half times height times length. So the formula is half times height, which is 4f, and the length, which is x. Hence we get this formula. Here is an example. The original length of spring S is 20 cm. So I will write this. If this is in the exam, I will suggest you to write this one original length. So this one is LO, original, O for original. When the final force is 20 Newton, so that's the force. Hence its new length becomes 12 cm, so that's new length. Calculate elastic potential energy. So you must write equals to exactly half fx, but we don't have x right now. So what's the x? So find x first. So in order to find x equals to length original minus new length. Original length is 20 cm minus 12 cm. So that gives us 8 cm. But if remember this one is unit joule, so we must change times 0.2 meters, and that is 0.08 meters. So half times 20 Newton times 0.08 meters. That gives us 0.8 joule. Okay, now let's move on to kinetic energy. Kinetic energy is half mv squared, and m is the mass in kg. Okay, let's solve the problem. Okay, so now first, question wants how much Ke. Now, kinetic energy equals to half mv squared. We have the mass, which is 500,000 kg, but we don't know the V. We know the V, however the V is not in SI unit, so we have kilo here. So we have hour. We have to change this one into second, and then this one into meter, because kinetic energy is in unit joule. So once, if you want to change that, Therefore, we put here 100 meter per second. Don't forget to square it. And you get this calculator and you get the answer to the power of 9 joule. So that's the answer. Let's try another example. A ball bearing of mass 0.2 kg. So this is the mass and this is kinetic energy. What is the velocity? So the solution is, we know that kinetic energy equals to half mv squared. So we substitute everything. Half 0.2 kg times v squared. Now we want v squared, therefore v squared equals to 3.6 joule over 0.1 kg, and that is equals to 36 meters squared as negative 2. Hence v equals to 36 meters squared as negative 2 square root, and that gives us 6 meter per second. Okay, let's work this together. Force exerted on a plank to compress a spring, given that the original length, final length, and final force. So here is another example. Remember, first you must write the formula, which is what's the formula? Yep, think. Okay, so the formula is half Fx, that's right. So what's the F? Given 20 Newton, and X exactly L naught minus L, and that is 50 cm minus 30 cm, 10 Newton times 20 cm, or maybe we can just write here so here is centi, so we have changed that one, right? So 1 2 so yeah, 20 times 10 to the power negative 2 gives us 2. So this is the best way to do it. Okay, and then when 10 times 0.2, so we get the answer as 2 Newton meter. Okay, now question number 2. Why are heavy vehicles shown in figure 2 usually of low velocity but possesses high kinetic energy? You have seen this on the road, right? It moves very slow. So formula of kinetic energy equals to half mv squared. So although the velocity is very low, however it is very big, therefore the mass is very high, hence the kinetic energy will be high. It's because of the very large mass.